Right. In today's session, we can try this question. Actually, now to compute these angles, right? So we have this diagram, circle, and actually we have, I think, three triangles because QSO triangle, OSP, and also the bigger triangle, QSP, QSO, OSP, and QSP. Those three triangles and the circle. But how would you compute these angles? That's the question. So we have that angle QPS, measure of QPS, that's 60 degrees. So we can use that, but that's not sufficient to compute all the other angles. Therefore, we need theorems, basically circle theorems. So to solve this, initially, this statement is quite important. O is the center of the circle. So O is the center. Therefore, and also PSQ are points on the circumference. Then what you can say about this line, QP line, or if I draw another line like this, through O, yeah, like this, or a line like this, chords, but that's the biggest chord that one can draw, the greatest, the largest chord, that's the diameter. All of these lengths are diameters, basically the same length. Hence, QP is a diameter. And more importantly, focus on this part now. So since QP is a diameter, what do you think about this part? This yellow colored circle, actually that's a semicircle. Why? Because QP is a diameter. Right? So now focus on that semicircle because we do have a theorem for semicircles under circle theorem. So that's the idea. That's the idea that I'm going to use to compute angle, right? So for semicircles, for a semicircle, so here's the diameter. Definitely diameter should go through the center like this. Then this is a semicircle. And also the bottom one is also a semicircle, right? And you might have seen this. If I draw a triangle using endpoints of the diameter, PQ like this, then the angle, this angle equals to 90 degrees. So that's a theorem. We can use that. So PSQ equals to 90 degrees. What's the reason? What's the reason? Angles in a semicircle. So you can use that to solve problems, right? Doesn't really matter what's the point you use. For example, one can draw a triangle like this. Like this. Let's say PMQ. That's also 90 degrees. Because still we use that P and Q, those 2 points, and another point on the circumference, point on the semicircle. You can draw so many triangles like that, and you will get 90 degrees each time. And also for the bottom circle, bottom semicircle, sorry, like this, till 90 degrees. PNQ, right? But initially check whether that PQ is a diameter or not. Right? Because if PQ is not a diameter, you can't use this. Because then the bottom part, so the upper half, not going to be a semicircle, right? So PQ should be a diameter. For that, that line, PQ line should go through that center O. For example, if I draw a line like this, that's not a diameter. So therefore, you can't use that line. Okay. Now, let's apply this idea for our problem. Angles in a semicircle. So we found our semicircle, that is PSQ. I think now it's very obvious. Now it's very obvious that this angle, this one, should be equal to 90 degrees, right? Because again, angles in a semicircle, right? I think you can understand that. So PSQ equals to 90 degrees. What's the reason? Angles in a semicircle. Now that's a very good starting point, because now we can use that to compute all the other angles, because 60 degrees is not sufficient to compute all the other angles. So now we found another angle, which means we can compute SQP angle very easily. What do you think? So this one equals to 90 degrees. Now we need this one. For that, we can use a triangle. I initially mentioned we have 3 triangles here. So we can use the bigger triangle to compute SQP, right? Okay, I'll show you. Right, we found this angle, that's 90 degrees, the top one. And also, this is 90. And clearly, using PSQ triangle, we can compute this angle. Let me mark that, this one. Because I'm going to use this triangle, the bigger one. Then the sum of interior angles of a triangle equals to 180. Hence, 90 plus 60 plus that unknown angle equals to 180 degrees. Then solve this one for SQP. 150. I can move that to the other side. SQP equals 180 minus 150, that's 30 degrees. Then to compute PSO, now what do you think? Now focus on that small, there are 2 small triangles. What do you think about PSO triangle? This one, the green colored one. Yeah. Now, if I join this point O and another point on the circumference like this, let's say OM, that length is same as this length. And this length. And this length. Why? Because OM, ON, OW, OY, those are radius, same length, right? The distance from center to the circumference is always a constant for a circle. Hence, OP and OS also, OP and OS should equal because that's a radius. So OP equals to OS. Hence, I can, okay, OP equals to OS. Therefore, I can mark that using a symbol like this. In other words, this is an isosceles triangle. Hence, the opposite angles should equal. Opposite angles of equal sides. So the opposite angle of OP side, we can mark that like this. That's the opposite angle. That angle and the opposite angle of this side, that is 60 degrees, should equal. So therefore, this angle PSO should equals to OPS. Because opposite angles, equal sides. We have OPS, that's 60 degrees. So let me replace this. OPS by 60 degrees. Therefore, PSO equals to 60. 60 and 60. So that's the answer for part C. Yeah. For part B, we found SQP, that's 30 degrees. Then we can easily compute SOP using the same triangle because we just have one unknown angle. I'm talking about that triangle. So you can compute this one because sum of interior angles equals to 180. Now we have 60 and 60. So the other angle should also equals to 60. In other words, quite interesting, that's, I think, that's an isosceles, not an isosceles, actually equilateral triangle, 60, 60, 60. Yeah. That's a bit strange, actually. Yeah. Okay. So can you understand that? POS plus 60 plus 60 equals to 180. From that, POS equals to 180 minus 120. That's 60. Right. Then that is POS. Then easily you can compute SOQ and OSQ. We can discuss that.